that work? Yeah. Okay. Then let's start with the presentation. I am really happy that we have Elias and Anthony here to present their thesis work, which was on spatial unconstrained gaze tracking for resource-limited devices. And they have really nice results, as you will see, using just a single camera and basically seeing where people are looking at. So I will give over to you guys, and questions can be in the end or anytime, guys. Go.
Thanks. Hi, and welcome to our master thesis presentation in spatially unconstrained gaze tracking for resource-limited devices. I'm Anthony, and my co-presenter is Elias. We've spent the last semester researching and developing a gaze tracking system that is capable of measuring and tracking where a person is looking in real time. We'll start with a brief introduction to the gaze tracking history to give you a broader view of the subject. So, in the 1980s, gaze tracking was heavily constrained. Some solutions had users to wear devices to align cameras to their eyes. Due to restrictions in computational power, the solutions were required to be computationally inexpensive. The important takeaway here is that the problem was heavily simplified. Input data had little noise, and all pre-processing was done beforehand. 20 years later, and gaze tracking had become more free form, requiring less constraints on the environment and typically not intrusive. Methods during this period have similar accuracies as in the 1980s, but they are less constrained. In the example image here, the system allows for some head movement since it will automatically detect the iris and corneal reflections. And then fast forward to today, and the gaze tracking problem has become incredibly unconstrained. The gaze trackers of today are very robust, allowing for use in different environments and allowing for partial or full visual blockage of features. A significant difference is that the subject is not constrained to be in the center of the image as previously required, and gaze trackers often allow for several people to be included in each image. As in on the image to the right, the gaze tracking can be used in the wild, where no per person calibration is required, and the camera can be placed however relative to the subjects. One of the main gaze tracking methods is the model-based trackers, which were one of the first to be introduced and are still used today in devices like the Tobii eye trackers. As the name suggests, the method uses mathematical models of an eye to determine the gaze and can take into account person-specific parameters. Model-based trackers are one of the most accurate gaze tracking solutions available, often reaching sub-1 degree accuracies. However, there are significant drawbacks with model-based solutions. They are not as robust as other solutions, as they are highly susceptible to the environment, lighting conditions, camera placement, and head pose. Additionally, they often require specialized hardware such as infrared lights and infrared cameras to operate. Although they can reach extreme accuracies thanks to the modeling of the internal eye, this also means that the model-based solutions require per-person calibration, as important eye parameters differ from person to person. These drawbacks limit the method to situations where the environment can be more constrained, such as laboratories or desktop usage. Another popular method is the appearance-based gaze tracking, which has been heavily researched for the past years in the gaze tracking field. It differs from the other methods as it finds different features in the eyes and face and creates a model to correlate these features with the subject gaze. There exist many different tools that can be used for this, like random forest regression, k-nearest neighbors, Gaussian processing, and deep learning. And a conceptual difference compared to other methods is that appearance-based gaze tracking is data-driven. This allows the method to be less affected by noise, as it can train on noisy data and approximate gaze angles better when features are missing or obstructed. So to summarize a bit, we have gone from controlled environments, intrusive systems, which also require per-person calibration, to in-the-wild gaze estimation, where noise and environment conditions do not affect gaze tracking. Most notably, gaze trackers today allow for multiple people at the same time, which also implies that the subjects are not required to be centered in the image. Therefore, we see that gaze tracking has become a two-stage problem, of first finding each subject in the image and then applying gaze estimation individually on them. Appearance-based gaze tracking utilizing deep learning has shown exceptional abilities on unconstrained in the wild gaze tracking, which is what we will continue with in our work. This leads us well into the objectives of our thesis. First, we are to implement a full gaze tracking pipeline. That means everything from reading an RGB image from a camera to computing the gaze for each individual. The gaze tracker should have competitive accuracy to recent works and be capable of 360-degree tracking in the world. To niche ourselves further into the subject, we have two additional objectives. First is to deploy and run the pipeline in real time on a Jetson Nano, a resource-constrained IoT device. This shows that the gaze tracking solution that is created is not just a proof of concept, but a deployable solution. Few works have shown real-time results. And finally, we want to investigate the effect of curriculum learning in the field of gaze tracking. Curriculum learning is an exciting method to increase accuracy by ordering your datasets and has had success in other domains. But to date, no other work of our knowledge have used curriculum learning for gaze estimation, but we'll come back to that a bit later. So now you know a bit about the background of gaze estimation. We'll start with our method and how we did our work. We'll start with the head detection network. And as we mentioned previously, recent gaze tracking has become a two-stage problem. Therefore, localizing subjects is an essential part of appearance-based gaze tracking. Compared to other relevant works, which rely on face detection, we want to accomplish unconstrained gaze tracking, including when the subject is looking away from the camera, a head detector is more appropriate. YOLO V5 was chosen as the head detector as it's a well-known object detection network, which can also be sized down for smaller systems. We use transfer learning and fine-tune the network on the Hollywood Heads dataset, teaching the network to create bounding boxes around people's heads. Going onwards with the gaze tracking networks, we evaluated several networks to select the most appropriate one for our lightweight gaze tracking pipeline. The chosen networks for this comparison was ResNet 18, ResNet 34, and MobileNet V2. These networks were chosen for two reasons. First, these networks are well known and are common in computer vision related tasks. Second, they're all designed to be at the lower end of the spectrum regarding inference time. Thus, they can be considered lightweight networks. Now that we talked about the models and networks we're going to use, we're going to shift our focus to the datasets. So the backbone of deep learning projects are the datasets. Quality data can compensate for a bad model, but not the other way around. As this project aims to create a spatially unconstrained gaze tracking pipeline, which works in the wild, the dataset needs to reflect that. Gazes of people in natural environments where information can be obstructed and noisy. This criteria led us to the Gaze 360 dataset, with its extensive variation in subjects, head poses, environments, subject to camera distance, and illumination. It captures the full 360-degree range of head poses, including images where the subject is looking away from the camera. Due to its variety, it is very suitable for in-the-wild gaze tracking. However, looking at the yaw angle distribution for the dataset, it's somewhat lacking in samples where the subject is looking towards the camera. To complement the Gaze 360 dataset, the MPII phase gaze dataset was also used in this project. It also features data captured in varied lighting conditions and head poses, however, focusing on screen-based gazes, meaning it contained gazes mostly looking towards the camera. We expect by combining these two datasets that the robustness and flexibility of the Gaze 360 dataset can be preserved, while improving the accuracy for front-facing images. So here are some samples of the two datasets. We can clearly see that they have some qualitative differences, both in features and image characteristics. For example, the MPI phase gaze dataset has black borders around their subjects, and the head area in the image compared to the image size also differs. Some of them are zoomed in more than others. So before we can use the datasets to train, we first pre-process them. So here we have 3 images as an example. And first and foremost, we apply the black border removal algorithm. And it's a simple threshold algorithm. So if a pixel is above a certain brightness, it's considered to belong to the subject. And for all of those pixels which match that, we calculate the bounding box around the subject. So now we have images that look like this. And then, as I mentioned, we normalize the head area. And on the examples here, we can see that the relative head area on each image is different. And early tests suffered from worse accuracy when the head area ratio in the training images differed. The drop in accuracy could be due to worse generalization because the networks had to learn to handle different head area ratios, thereby increasing the difficulty of the problem. To mediate this, we ran each image in the dataset through our head detector and using the resulting bounding box to crop the image. This would normalize the head area and also have a consistent head area to when the data comes live from a web camera. Additionally, as you may notice, is that sometimes the head detector finds the wrong face in the image for various reasons. And for this, we check that the face that was found is in the center of the image. And if not, we will remove it to remove falsely detected heads. Like this. Now we're on to the curriculum learning part. And before we go through how we used it, we will give you a quick background on what curriculum learning is. So curriculum learning takes inspiration from the human learning process. In standard training, data points are sampled randomly from a dataset during training. Curriculum learning instead orders your data from easy to hard so that you start with easy examples when training your network, and then with time, you start to add more difficult examples from your dataset. It has been shown to have a more positive impact on training time and final model accuracy. So to perform curriculum learning, we need to define 2 functions. First, you have the scoring function, which will define the difficulty for each data point and will be used to sort the data. Then we have the pacing function, which defines at which pace the more difficult data is added during training. So to evaluate curriculum learning for gaze tracking, we tested 2 different scoring functions and 1 pacing function. The first scoring function uses bootstrapping to define the difficulty. In bootstrapping, you train the network normally, taking random samples from a dataset. When finished training, you run through the entire dataset and measure the error that the network gets on each data point. This error will define the difficulty for that data point. The higher, the more difficult. And this will be then used to train a new version, which will train using curriculum learning. Then we have our human-based scoring function, our heuristic, where we've defined that the difficulty of a data point corresponds to how far away someone is looking from the camera. The idea is that as you look further away from the camera, less information will be available to the system as important features become obstructed. The pacing function we chose was a single-step pacing function. Here, an initial percentage of the data is available at the start of the training, and then later on, at a certain point, the remaining data is added. There were other pacing functions that we could choose, but we chose this one to reduce the amount of tuning needed, as it has fewer hyperparameters. Additionally, there wasn't a significant accuracy difference compared to other pacing functions. So to evaluate the curriculum learning, and to make a fair comparison, we did these 3 configurations for each network. First, we trained using a standard training method, so we randomly sampled from data, and this was our baseline. Then, of course, we have our curriculum learning. Here, the data is ordered from easy to hard, and what we want to see here is that it gets better, it achieves better accuracy. And then to validate this, we added anti-curriculum. Here, you reverse it so that you start with harder data and then with time introduce easier data. Ideally, if curriculum learning increases the accuracy due to ordering the data, then anti-curriculum should decrease the accuracy. If not, there may be another factor which impacts the result. We also performed hyperparameter optimization on our tests. Comparing networks and training methods is a complex task. There are many variables and factors which can impact the result. One of these are hyperparameters, and they control the training parameters of networks, such as epochs or learning rate. To further rigorize our comparisons, we do this hyperparameter optimization so that we can achieve full potential on each network and training method. If hyperparameters are badly tuned, then the network will perform well below its potential, which will not make the comparison fair. There are many ways to perform hyperparameter optimization, and we've chosen Bayesian optimization as is the most efficient method in regards to the number of samples needed. And for the comparison, hyperparameter optimization was done for each training method and neural network. Finally, before we go into the result, we'll talk briefly about how we optimize models for the hardware. We used NVIDIA's TensorRT framework to deploy models on the Jetson Nano. It combines operations that are commonly used in machine learning and map them to hardware functions, meaning that we can reduce the number of operations that the hardware needs to execute, and thereby making the inference time lower. NVIDIA TensorRT can always also lower the memory footprint, making it easier for you to fit models onto embedded devices. So now we've talked about the history of gaze tracking and how we've done it in our project. And now Elias will take over and go through our results.
Yes. So hi. Now we have gone through the context of this project, as well as the methods we've used in order to fulfill the thesis objectives listed earlier. So moving on to the results. The results have been split up into 3 different parts. So we will start by looking at the gaze tracking pipeline. Then we'll look at the network comparison. And at last, we will look at the results from the curriculum learning investigation. So on the screen, you can now see an overview of the performance of the gaze tracking pipeline. So starting with the speed. When running real-time gaze tracking on the Jetson Nano with images containing a single subject, the complete pipeline achieves between 14.9 and 17.2 frames per second. depending on the model used for gaze inference. So to achieve these numbers, both the YOLO head detection model and the gaze inference model were using TensorRT, and the complete process of data pre-processing, head detection, cropping, and gaze inference is included. As the Jetson Nano is a resource-limited device, we consider the goal of creating a lightweight gaze tracking pipeline fulfilled based on these numbers. In terms of accuracy, the mean angular error ranges from 13.86 degrees and 15.09 degrees. And this might sound a bit high, but it should be noted that the test dataset is a subset of the Gaze 360 dataset, which contains the full 360-degree range of head yaw angles, meaning that some pictures, as you have previously seen, only shows the back of the subject's head, which carries an inherent uncertainty. So as the mean angular error lies in a similar range as the numbers achieved by the Gaze 360 model, we consider the goal of achieving competitive accuracy to also be a success. To get a better feel of the performance, we'll show some images of the pipeline in action. So to explain what you're looking at, the arrow obviously represents the direction of gaze estimated by the pipeline. And as the arrows are two-dimensional, the color of the arrow simply represents the depth. That is, a red arrow will be looking towards the camera, and the blue arrow looks away from the camera and into the image. The green circle you can see represents the uncertainty of the estimation, where a larger circle means that the model is more uncertain about the estimate. So looking at this image, for example, we can see that the model is far more confident about the estimate of where Jon Snow is looking, where we get a good look at the facial features, compared to the estimate of Theon Greyjoy over here, where the model is quite understandably very uncertain. So with these different images, we wanted to show the robustness of the pipeline, because all of the images shown here would be considered hard for traditional gaze tracking purposes, and that is for several reasons. For one, the subject often takes up only a small part of the image, rendering the head crops quite low resolution. There is also plenty of facial occlusion, where parts of the face are not visible. And note that even when accurate gaze estimation is impossible, such as when the eyes are not even visible, then the pipeline can still make decent best guesses. So now a quick run through of the technical part of the pipeline. So the gaze estimation pipeline consists of the necessary steps to infer gaze for each person in an image. A flowchart of the pipeline can be seen in the slide, where the sampled RGB image is fed into the head detection block, which returns a pair of bounding boxes and head images, one for each found subject in the image. This output is passed into the gaze estimation block, which outputs the gaze and uncertainty of each head image. So looking a bit closer, we have the head detection block here, which, as the name suggests, is responsible for finding all heads in the image and inferring their respective bounding box. And as you can see in the slide, the YOLO V5S network is the centerpiece of the block, and it detects the head bounding boxes and their confidence values. Because the YOLO network may find some false positives, which is detections that do not contain a head, and the confidence threshold is therefore used to filter out false positives in the post-processing of the detections. An extra step is also done to crop the input image by each bounding box, which extracts the head images. And finally, then, both the bounding boxes and the cropped images are outputted from the block. On the Jetson Nano, the YOLO head detection using TensorRT achieves an inference time of about 40 milliseconds. So moving on to the other major block, the gaze estimation block. And this is the last stage of the pipeline, and it receives a cropped RGB image, which should only consist of a person's head. During pre-processing, the image is scaled to fit the input size of the gaze network, which for all models used in our project is 224 by 224, and the color values are then normalized. The pre-processed image is then fed to the gaze estimator, which in turn outputs the gaze estimation in terms of yaw and pitch and the uncertainty. So to summarize the gaze tracking pipeline, we feel that our goal of designing and implementing a lightweight gaze tracking pipeline with competitive accuracy to similar models can be considered fulfilled. As shown in the images of the pipeline in action, it is robust and it can handle quite complex situations where faces are blurry or partially covered with surprising accuracy. And even for the really hard cases, the pipeline can make decent best guesses. The pipeline has also been successfully deployed on an edge device, more specifically the Jetson Nano, and can on that platform estimate gazes from a live camera feed with acceptable real-time performance. And finally, there are still much room for improvement. The current implementation lacks any depth perception, meaning that the pipeline cannot infer what point in the environment the subject is looking at. And this will be further discussed under future work. And this project has also mainly been focused on optimizing the two major parts of head detection and gaze inference. But there are ways to optimize the entire pipeline through, for example, the NVIDIA DeepStream SDK, something we will also come back to in future work. So moving on to the network comparison that was performed as a part of this project. As you might remember, the three networks used was ResNet 18, ResNet 34, and MobileNet V2. And starting with the accuracy, the three different networks went through a Bayesian hyperparameter optimization process where around 220 different configurations were tested for each network. The best performing configuration was then evaluated on the test set, and the results can be seen in the plot. So what we can see is that MobileNet V2 achieves the highest mean angular error out of the three tested models. The ResNet networks both perform better, and the ResNet 34 achieves the lowest mean angular error. So from just looking at this plot, it might seem clear-cut that ResNet 34 is the best option for this project, but as the target application is lightweight and fast gaze tracking, inference time of the models also needs to be taken into account. So to compare inference times, two different hardware platforms and three different environments were used. We have the desktop environment using PyTorch. We have the Jetson Nano environment using both PyTorch and TensorRT. And this setup allowed us to analyze the speed of the networks from multiple perspectives, as well as getting a fair comparison between PyTorch and TensorRT. All inference time comparison does only include the inference time of the gaze inference network. That is, no pre-processing of the data or head detection is included in this. So on this quite busy slide, you can now see the results from the inference time testing in all three environments. So the leftmost plot here shows the numbers for the desktop environment using PyTorch. The middle plot shows the numbers achieved for Jetson Nano using PyTorch. And the rightmost plot shows the numbers for Jetson Nano using TensorRT. To summarize, we can see that ResNet 18, here, here, and here, is the fastest network in all environments. And interestingly enough, by comparing the leftmost plot to the two other plots, we can see that MobileNet V2 is slower than ResNet 34 in the desktop environment. However, on the Jetson Nano, the opposite is true, and ResNet 34 is instead the slower network. And this might seem strange, but we have found the same pattern in other research where MobileNet V2 does not efficiently use more powerful hardware. Our hypothesis is that the reason for this discrepancy is the extensive use of one-by-one convolutions found in the MobileNet V2 network. These have been shown to lack cache efficiency, and that inefficient use of cache would be punished harder in the desktop environment as the computational time is already very low. Looking a bit more closely at the impact of TensorRT, we can see that the speed increase is significant. And as the speed increase is around a factor of 3 for all models, the absolute difference between the networks also decrease significantly. And this is interesting for us as it opens up for the slightly larger models, such as ResNet 34, to also be reasonable choices in this kind of resource-limited environment. It should be noted here that TensorRT is a powerful and complex tool, which allows the user to optimize their deep learning models to a high degree. So the inference time that we have presented here for TensorRT could most likely be further decreased given the time to do an individual in-depth optimization process for each of the 3 chosen networks. But nevertheless, the plot shows that even without such an in-depth process, TensorRT can be very beneficial. So to summarize the network comparison, MobileNet V2 gets outperformed by ResNet 18 in both metrics, and thus it's hard to consider it the best option. It should be noted that MobileNet V2 has a smaller memory footprint compared to the ResNet networks. And this, in some cases, this could be very useful in similar applications if memory usage becomes the bottleneck. The ResNet architecture, however, seemed to be a good fit for this domain. Whether ResNet 18 or ResNet 34 is the better choice is not very clear though, because ResNet 18 is faster, but ResNet 34 is more accurate. And here it basically comes down to a choice between speed or accuracy. We also found that seeing which network is faster in the desktop environment is not necessarily a good indicator for the performance on more resource-constrained devices, as the slowness of MobileNet V2 and ResNet 34 kind of switched when we switched to the more resource-constrained device. And finally, we saw that TensorRT significantly speeds up the inference process and is almost necessary when deploying computationally demanding machine learning applications on resource-limited devices. The final part of the results comes now, where we will present our findings from the curriculum learning investigations. So as you might remember, 2 different scoring functions were evaluated. We had bootstrap scoring, where the network itself defines the difficulty, and we have gaze angle scoring, where the gaze angles away from the camera determines the difficulty of the data. The bootstrap scoring shows a positive effect, where the corresponding to these 2 bars, by the way. So it shows a positive effect where the curriculum training slightly reduced the error and the anti-curriculum training slightly raised the error. However, the difference here is very small, so we are hesitant to make any big claims about the effectiveness of this training method. Further investigations here would be needed, where maybe more complex pacing functions are evaluated. The gaze angle scoring seems to be a better way to score the data in our setup, and the positive effect on accuracy is much more prominent here. So to summarize, we found that curriculum learning can have a positive impact on the final accuracy in this domain of spatially unconstrained gaze tracking. The results also imply that the gaze angle away from the camera can to a reasonable degree approximate the difficulty in this kind of data. And this seems logical, but was not necessarily self-evident, as many considerations that reasonably should have an impact on difficulty, such as bad lighting conditions, motion blur, occluded facial features, are not taken into account with this scoring function. And finally, we conclude that further investigation would be interesting. And while the impact of curriculum learning were not huge in this project, one should remember that being able to increase the accuracy, if even slightly, without any modification to the model or dataset is still a very powerful concept. And such continued investigations could research different scoring functions and more complex pacing functions, which have been shown to further increase the accuracy in some cases. So the last part of this presentation is a bit of future work. We will highlight 3 interesting ideas that we feel could be the next steps in this project. Starting with other difficulty-based training methods. It would be interesting to further investigate the concept of difficulty by testing other difficulty-based training methods. 2 methods that comes to mind are hard example mining and focal loss, which both use the concept of difficulty when designing the training routine. The interesting part here is that while curriculum learning mainly focuses on the easy examples, these methods instead focus on the hard examples. So focal loss adds weight to the loss of each data point so that harder examples could create larger changes throughout the network during training. In hard example mining, the network is trained as usual, but at the end of training, the model is then fine-tuned with only the most challenging examples. Next up, we have depth estimation, which have been mentioned earlier in this presentation, because this thesis is solely focused on the direction of gaze, which describes where the subject is looking towards. And this contains much helpful information, and it could tell, for example, what part of the shelf that a customer is looking at in a store. However, to find the point in the environment that the subject is looking at would require information about the distance between subject and camera. So adding depth estimation by the use of, for example, an RGBD camera, like the Microsoft Kinect, would be an exciting way to continue this project. This would not only allow the gaze pipeline to estimate the point in the environment where the subject is looking at, it would also open up new possibilities to include this depth data into the training, which might improve the robustness and accuracy of the model. And then finally, we have NVIDIA DeepStream. And the DeepStream SDK is a collection of development tools that gives users ability to optimize all steps in a deep learning computer vision pipeline, from the fetching and passing of the input image to the on-screen display of the results. DeepStream also supports running inference on multiple models, either in series or in parallel, in an optimized way. And as has been mentioned previously, this project focused on the two core components of the gaze tracking pipeline, head detection and gaze inference. And thus, DeepStream could be useful in further improving the speed of the whole pipeline by, for example, reducing the overhead cost related to passing information between CPU and GPU, or by optimizing the retrieval of images, optimizing post-processing, or as well as the displaying of the output. And by that, our presentation is concluded, and we want to thank you very much for listening. And we also want to thank everyone here at Knightec for giving us the opportunity to do this project. Any questions or feedback we are ready to take on right now.
I want to say thank you, first of all. It was a great presentation. Very nice.
Thank you.
Thank you.
Yeah, I also appreciate that it was understandable for someone that haven't worked with this for a while. So that was really good.
Okay, that's great to hear. That's one of the hardest things to estimate, I think.
Yeah, we put a lot of effort into that.
Yeah, great.
Yeah, one thing I want to just mention, what you didn't show now was the video you made with a simulator, no?
Yes, exactly. Yeah. We skipped that part.
They also used a car simulator in Chalmers, and basically did eye tracking, and then they overlaid the video with the tracking position. That was actually really cool to see exactly where the person is looking, which was actually one of the use cases that we wanted to investigate. How would this work in a car? And that was actually really impressive. I mean, it was not with any reference or so, but it looked natural at least. Yeah.
So you kind of missed that part in the presentation after knowing the report. Then we might add it back. We had it initially, but removed it to cut some time.
I don't know. Do you have in the report? I remember you showed it in a meeting we had before, but I mean.
Oh yeah, okay. You mean the actual video where we overlaid the?
Yeah.
Okay, yeah, that we haven't mentioned in the report actually.
Yeah, and here neither. So that is really cool. This is something that could go in a presentation. I mean, of course, it's not.
Yeah.
Just representative, but it's really a real world application. Even though it's a simulator, but.
I mean, that's good feedback. We might add something about that.
Yeah, I think the reason was that there were so much things that we haven't calibrated, so we're really unsure how well it worked, exactly. So I think that's why we haven't spent too much time on it, having other stuff to do.
That's fine. I mean, yeah, you had a lot of stuff you did. I mean, with the computer networks that you used for the hyperparameters, basically to optimize them, and curriculum learning, and you made the simulator, and yeah, you worked on a lot of stuff. I mean,
yeah.
So it's good to maybe slim it down a bit to the important part, which you did. I mean, you focused on the curriculum learning mainly. That was good. I think it was very nice. Okay. Yeah, then if there are no questions, I mean, it's basically just you guys and Walter and Jakob is also here still. So if nobody in Delhi, Frederick also, but if nobody has a question, then we can also just close the meeting here. I can stop the recording and yeah.